Ocean currents act as a global conveyor system. They redistribute warm and cold water across the globe. And these currents moderate our climate in very specific ways. So, for example, the Gulf Stream, seen here, keeps Northern Europe much warmer than Northern Canada. Variations in ocean salinity and density can help drive ocean circulation. It is important to remember that there's a difference between weather and climate. So let's discuss those differences. Weather is what you get. These are the conditions of the atmosphere over a short period of time. The weather, as we know, can change within minutes or hours, meaning that if it's really stormy on Saturday, the weather can change to be sunny and cheery on Sunday. Now, climate is what you expect. This is how the atmosphere behaves over a long period of time and space. The average regional weather pattern over decades is what we're talking about when we're talking about climate. But we can also stretch that not only from decades, but also through centuries. So when we look at this on a time scale from hours, days, months, years, decades, all the way to centuries, we transition from weather, climate variability, and then finally climate change. And below here, we have examples of what those mean and how those changes manifest. So on the scale of hours within the realm of weather, that means raining or sunshining. In the scale of days for weather, we have cyclone events. On months, could be wet or dry season. Then when we're talking about decades and decadal events, these are things like El Nino and ENSO. And then finally, when we're treading over to the change in climate over centuries, that's things like global warming, sea level rise, and ocean acidification. These are all things that we are seeing manifest in our world today. But we do know that climate has changed over time. And the stability of climate depends on the temporal scale that you're looking at. So over centuries and millennia, we know that climate has changed. We know this in large part by examining data that is within ice cores and has been preserved for us to investigate. So the question is, if climate does shift, how fast might it change? And what will those changes mean for the environmental systems that we depend on? So how fast does it change and how big are those swings? We can look at lots and lots of data, not only from ice cores, but also ancient coal deposits, desert deposits, tropical soils, glacial material, and map out how temperature has changed throughout geological time. So here we have age in millions of years from the most recent here all the way to the Archean period. We have mean global temperature, cold periods on the left, warm periods on the right, and then mean global precipitation with dry periods on the left and wet periods on the right. So what we see in this graph is that yes, there have been large swings in temperature throughout Earth's history. But for the past 1 million years, CO2 concentrations did not surpass 300 parts per million. And as we learned several slides ago, we're at over 400 parts per million today. CO2 concentration does have a direct effect on temperature, and we'll see that on the next slide. But this is just to show you that there has been both cold periods and warm periods on Earth. And believe it or not, we are currently in a cold period. For example, if we were to take a look at the type of climate that the dinosaurs experienced when they were on Earth, just before they went extinct about 65 million years ago, we are basically in a refrigerator compared to then. So let's take a look at the correlation between CO2 concentration and temperature. This is work that was published about a decade ago from an expedition in Antarctica. And this was the European Project for Ice Coring in Antarctica, or EPICA. And they produced a record reaching back over 800,000 years. and they publish their work in Science. So these cores can show us that not only has climate changed dramatically over that time, but there is a close correlation between atmospheric temperature and CO2. So if we take a look along the time scale here, remembering to add 1,000 after this number, we can see temperature change in degrees C in blue, and we can also see CO2 change in parts per million in the red lines here. So from these Epocha ice cores, we know that CO2 concentrations have varied between 180 parts per million to about 300 parts per million in the past 800,000 years. Therefore, we know that today's concentration of over 400 parts per million are about 1/3 higher than the Earth has seen in nearly 1,000,000 years. It is rising at a rapid rate at about 2 parts per million per year. We can do this type of analysis not only for carbon dioxide, but for other greenhouse gases like nitrous oxide and methane. So let's take a look at how we look at these gases. It's actually really cool. The scientists are able to measure directly the trapped atmosphere that is found in air bubbles in these ice cores. So each bubble here preserves the atmospheric concentrations of the gases in the atmosphere at that time, including things like methane and carbon dioxide. So what I'm going to show you here is analysis that bridges the Epocha samples with some other samples and shows atmospheric measurements of carbon dioxide and methane through time. Now, we're not going back in this analysis the entire 800,000 years. We're just focusing in on the last 1,000 years. So what we see here for methane is that during this 1,000 year period, we really didn't change the concentration of methane much. It hovered about 750 parts per billion. But what do you notice? We have this extreme uptick in parts per billion concentrations in methane shortly after the Industrial Revolution. So here we have clear evidence for the increase in methane concentration and the time it took to get from about 700 parts per billion to nearly 2,000 parts per billion. This, of course, can be directly related to human-caused processes like raising cattle, as we learned in several lectures ago now, I think, that cattle have methanogens, which are a special type of microscopic organism that make methane. So harvesting lots of cattle and rice paddies. Rice paddies are a large contributor of methane to the atmosphere, and other human activities. These all combine to lead to this rapid increase in methane concentration. We also see the same trend with our carbon dioxide concentrations as well. So we know that there are natural cycles on Earth that have changed the climate on Earth, specifically swinging us back and forth between glacial periods where the Earth was nearly entirely encapsulated by ice and snow to interglacial periods, which is what we are experiencing now. We do expect modest climate changes that correspond to this 11-year cycle in the sun's intensity. More dramatic shifts are actually caused by what is known as Milankovitch cycles or orbital cycles. There are 3 types of Milankovitch cycles: eccentricity, which occurs every 100,000 years, tilt, or obliquity, as it's also called, occurs every 40 to 41,000 years, and then wobble, or precision. That is on a 26,000 year cycle. So let's talk about what each of those mean. The first one is changes in eccentricity, or the orbital shape. Again, this is a 100,000 year cycle, and we have changes in Earth's orbit shape going from really elliptical to more circular. And the changes occur roughly every 100,000 years. So the change in orbit shape or eccentricity is the reason why we have seasons that are slightly different lengths on Earth. The next one is changes in the Earth's tilt or obliquity. Right now, we are at 23.5, I believe, which is roughly midway between the most extremes in Earth's tilt. This is on a 40 to 41,000 year cycle. And axial tilt is the reason why we have seasons on Earth. Finally, we have axial precession or wobble. This is a 26,000 year cycle. This makes the southern hemispheres hotter and moderates northern hemispheres' seasonal variations. Now, what's interesting, in about 13,000 years, in the northern hemisphere, we are going to be experiencing those hotter summers, and the roles here will be flipped. As we've already touched on, there's a lot of interactions between the atmosphere and the ocean that causes changes to the climate. Something that you've probably heard about is El Nino, otherwise known as ENSO, or the Southern Oscillation. This occurs in the southern hemisphere right around the equator here. And ENSO affects weather throughout the entire Pacific Ocean, causing heavy monsoons or even serious droughts. So mechanistically, what's happening? Under normal conditions, we have cold upwelling that drives the normal circulation of water around the equator that brings warm, dry subsistence to areas of South America and Central America. This is then carried across the trade winds to Indonesia, where we have a low pressure environment that brings rains. This then precipitates high altitude winds that then drive this entire circulation, all brought about through the interaction between the convection of the ocean and the convection of atmospheric winds. But during an ENSO event, we have weakened currents and no upwelling is occurring. So that's why, particularly right around the equator, we have this massive low pressure system that is bringing in all of these heavy rains, and monsoons will be incurred, but also can cause serious droughts in places of high pressure. So how do we know that the climate is changing faster than normal? We can look at specific trends in atmospheric gases, particularly tracing the change in CO2 alongside the change in temperature in our atmosphere. So the evidence that human activities are increasing atmospheric CO2 mainly came from an observatory located in Hawaii called Mauna Loa. Since 1958, this observatory has been taking measurements each and every day of atmospheric CO2. It was established by a scientist called Dr. Keeling. And so we call this data the Keeling curve. And the Keeling curve shows that CO2 concentrations have risen consistently and sharply ever since measurements started to happen. And we can map out the rate of this increase and see that it's increasing about 0.5% per year. So if you're curious, you can follow the Keeling curve on Twitter, where you get readouts of the parts per million concentration in CO2 each and every day. So we can trace the change in CO2 concentration in the atmosphere to the change in temperature directly and map them out side by side. So here in this graph, going from 1958 to 2018, we have in red the monthly mean CO2 concentrations. In black, tracing through that line, is the annual mean in CO2. And then in blue, we have the temperature representing the 5-year mean. So the first thing that you might notice is that we have these oscillations in CO2. If you were to zoom in, each and every year has an increase and a decrease. These are seasonal variations in the amount of CO2 that has to do with the productivity or the lack of oceanic productivity depending upon the season. So we can track that from 1958 to 2018, we have seen this extremely sharp increase in the amount of CO2 in our atmosphere, going from about 315 ppm when observations started to be made to today, where we know we're at about 415 parts per million. The data here stopped at 2018. So how does that track with our temperature increases? Well, we do see by and large that temperature has been increasing alongside increases in atmospheric CO2. There are bumps and wiggles, but by and large, the trend is undeniable. There's an increase simultaneously in both CO2 and temperatures. So the scientific consensus on climate change is absolutely crystal clear. Climate scientists worldwide have collaborated in collecting and sharing complex climate data and programming models to describe how the climate system works, both in the present, in the past, and in the future. Evidence shows minor differences among all of those models that are generated across the world, but there's no disagreement about the direction of change. There might be slight inconsistencies between the different models, but by and large, they all agree that climate change is happening right now. So the evidence shows unequivocally and undeniably that climate is changing, and the global average is a warming trend because of increased retention of energy in the lower atmosphere, caused mainly by greenhouse gases such as CO2. So what does the data look like? We can go to some really wonderful websites like the National Oceanographic and Atmospheric Association, or NOAA, and take a look at the long-term trends. So here we have differences from the average annual temperature from the year 1880 through today. So what we see from this graph is that the 10 warmest years on record have occurred in the most recent decades. So if it's above the average temperature, it's in red above the 0 degree line. If it's below average temperature, it's in blue below this 0 temperature line. So we can look at present and see, by and large, within the past 2 decades, we've experienced some of the warmest seasons on our planet. New monthly and annual records are increasing in frequency, and so we get to see in real time how this temperature change is playing out. And what we can do next, now that we know that through time these temperatures are increasing, the next question is, where are these temperatures increasing the most? And that, unfortunately, is in the Arctic. So this warming trend that we are seeing is concentrated in the Arctic Circle, particularly in areas like Siberia, northern Russia. So the scientists that study climate change are climate scientists that focus on specific areas that they have expertise in. The best type of science that can ever be done is collaborative and interdisciplinary. So the Intergovernmental Panel on Climate Change is the most comprehensive effort to describe the state of climate knowledge, and it is composed of scientists of all different fields around the world. The IPCC brings together scientists and government representatives from 130 countries, all with the unified aim to review the scientific evidence and the causes and likely effects of human-caused climate change. So they have put out a number of IPCC reports to date, but in 2007, the IPCC issued its 4th assessment report, and this was pretty much the bombshell report. The conclusion was that a 90% certainty that the observed climate change is caused by human activity. And subsequent reports have actually raised that to 99%. So what does this mean? This means changes in heat waves, sea level, and the frequency and intensity of storms. In that fourth IPCC report, they presented a variety of climate scenarios for predicted emissions of greenhouse gases. For each scenario, they modeled future emissions starting in the year 2000. Observations since the year 2007 show that all of the IPCC scenarios were actually too conservative. So the things that they predicted would happen, they happened, but actually at a much larger scale. This is everything from greenhouse gas emissions, the increases in temperature that we've seen so far, the increasing sea level that we have observed, and the energy use. All of this has accelerated much faster than IPCC projections. So what this manifests as is droughts, floods, crop failure, and waves of refugees, climate refugees. So the annual human-caused or anthropogenic CO2 emissions for 4 climate change scenarios are presented here on this graph. So we have the year 1950 all the way through projected 2100. And we have the annual emission of CO2 presented in gigatons per year. So let's unpack this diagram. Here in black, we have historical emissions of CO2. So that is what has already been observed. These different trend lines and the colors that are bounding each of those trend lines represent the projected CO2 emissions under different types of scenarios. So down here, the 0.3 to 1.7 degree C increase represents a scenario that involves aggressive and rapid reduction of greenhouse gases. A lot of mitigating practices are being taken into consideration, meaning that we are no longer following business as usual. There are all of these practices in place to lower the amount of projected CO2 in the atmosphere, which would then cause the increase in our temperature to be lower. However, up here at the top, the 2.6 to 4.8 degrees C increase in our globe represents the projection for business as usual. So that means all of the steps that are included in the Paris Climate Accords, all of the other city and state local mitigation practices are not being implemented or followed. We are consistently relying heavily on fossil fuels. This is the projected scenario for increased temperature on our globe. So I would like for you to read a number of sections in your textbook. The pages are located here, although I might have a different version of the textbook than you do, but still please read the case study that's in the chapter for this material, the key concepts, exploring science, what do you think, and what can you do? So let's focus on the impact again on that 1 meter rise of sea level that we started out with. Zooming in on Florida here, we discussed the economic devastation that would be wrought on Miami with the 1 meter rise in sea level. But we would also expect our other coastal areas like Louisiana and New Orleans to be impacted in similar ways. So the approximate change in land surface with 1 meter of sea level rise or 3 feet of sea level rise is a change that is likely to occur by the year 2100. And so our coastlines that we're used to seeing by and large are going to be completely reshaped and redefined by the year 2100 because of our sea level rise associated with anthropogenic climate change. If no action is taken to stop the amount of CO2 emissions in our atmosphere, sea level change might actually be greater than that 1 meter. It might actually be 6 feet or more. So unfortunately, even though the science is extremely clear and climate scientists have been basically screaming from the rooftops their assessments, policymakers have made little progress in finding solutions. Climate control, unfortunately, is a classic free rider problem in which nobody wants to take action for fear that someone else might benefit from their sacrifice. The question is whether the sacrifices need necessarily be as big as some policymakers suggest. Climate scientists point out that shifting our energy strategy from coal to wind, solar, with greater efficiency could actually produce millions of new jobs and save billions in healthcare costs associated with coal burning. So, all in all, it actually is cheaper and more job positive to address the need for green, clean energy in this country and across the globe. And these are many of the things that are outlined in the Green New Deal. So, the main anthropogenic greenhouse gases are CO2, methane, and nitrous oxide. And fossil fuel use is responsible for 80% of CO2 emissions. And this has been increasing since pre-industrial times. We've seen an increase in CO2 by 31%, an increase in methane by 151%, and an increase in nitrous oxide in 17%. CO2 is extremely important because of its abundance and because it lasts for decades or centuries in the atmosphere. CO2 is generated, of course, through emissions from transportation and energy, but also cement production furnaces and burning of forests and grasslands are also major sources of CO2. Together, these factors release more than 33 billion tons of CO2 each and every year on average. That's about 3 billion tons of excess carbon that needs to be taken up by terrestrial ecosystems or the oceans. And so that's a huge surplus that unfortunately we don't have the necessary sinks like the ocean to continuously count upon to keep sucking up that excess CO2. What people don't really recognize is that methane, CH4, has a warming power that is 30 times greater than CO2. So CO2 is what we always talk about and focus on, but methane is much more powerful when it comes to warming power. And unfortunately, if current trends continue, CO2 concentrations could reach about 500 parts per million. That is 2 times the pre-industrial level of only 280 parts per million. And we're talking about just the end of the 21st century. And it's not hard to imagine that we're going to get there because, as you remember, we're at 415 parts per million right now. And we can see this clearly when we take a look at the CO2 emissions, methane emissions, and nitrous oxide emissions going back through time, and especially since industrialization. So here we have carbon dioxide in red, we have methane in the dashed black, and nitrous oxide in blue. And so by and large, those levels remained steady for each respective gas up until you get to this tipping point right around the year 1880, where we reached industrialization. After that point, these concentrations all skyrocket all at once. So if you've ever heard about a hockey stick model, this is exactly what they're talking about. So imagine this is a hockey stick where the stick represents this massive increase in concentration in the gases that followed after this event of the industrialization period, which before that period, there was very little change. So this would be the blade part of your hockey stick. We can break down the contributions to global warming from these different gases. We can look at it both from gas to gas and the different sources, and then from decade to decade. So by and large, what we see is that in red, this CO2 from fossil fuel use has always made up the lion's share of the amount of heat produced on our planet. But what has been increasing decade after decade is this nitrous oxide from agriculture and other sources. So we really need to be mindful not only about the gases themselves, but the sources and the amount of warming that they are contributing. We can also look at who is making these emissions. And we have the US at 21%. We have China just above the US at 24%. And then all others, aside from Japan, India, Western Europe, and the Russian Federation, make up an entire quarter.